All right, guys, so today we are doing 7.3 lesson 6. So yesterday we tried to use evidence to answer the question whether or not chemical reactions were occurring in the mouth. And we should have question number 5 answered in our progress tracker. That question is, why do large food molecules like certain complex carbohydrates such as starch seem to disappear in the digestive system? So what do you think? Do you think chemical reactions are occurring in the mouth? What is your evidence for that? All right, let's talk about moving on. Do you think all of our food gets broken down in the mouth? Or what about the other food molecules that we eat, like protein? What happens to those? If they don't get broken down, where do they go? What happens to them? How could we figure it out? Well, that's what we're going to do today. So today we're going to be analyzing some food molecule data for a healthy person. That is this page right here. All right. And this page right here is your food molecule data for a healthy person. You are going to read the directions at the top, and you are going to fill out this table based on the graphs that you have in this packet, okay? So the light colored bar, the light green colored bar, shows the amount of the molecules in the previous location in the healthy person. The dark color bar shows the amount of the molecule in the new location. So it's your job on your table to record whether the food molecule increases, which you'll draw an up arrow, decreases, down arrow, stays the same, you'll draw an equal sign, or if it's at 0, you just draw 0. Okay? So, for example, from the graham cracker to the mouth, we did this one in class together, but let's take a look. For water, if we take a look at this chart, the previous location is the graham cracker, the new location is the mouth. So we're comparing the light green bar to the dark green bar. Is there any change? Increase, decrease, equal, or is it at 0? You'd put that in this box right here. Water, mouth. Because those bars are equal, there's been no change. So I'm going to write, you guessed it, an equal sign. How about the next one? Amino acids. Up, down, equal, or 0? You guessed it, 0. Protein. Increase, decrease, stay the same, or 0? Stayed the same. Fat, fatty acids. Increase, decrease, stayed the same, or 0? 0. Fat. Increase, decrease, stay the same, or 0? Glucose. Increase, decrease, stay the same, or 0? If you said increase, that's correct, because if I compare the light green bar to the dark green bar, the bar got bigger. That means it increased. Then I go to complex carbohydrates. What happened there? Decrease. Then I look at fiber. Equal. So what happened here? Why did glucose increase and other carbohydrates decrease? What happened was there was a chemical reaction in the mouth. Amylase in our saliva converts the other complex carbohydrates to glucose, which means the other complex carbohydrates decreased and the glucose increased because the amylase changed the other complex carbohydrates to glucose. It's your responsibility now to examine the rest of the graphs and complete the rest of this data table. You're comparing the mouth to the esophagus to the stomach to the beginning of the small intestine, the beginning of the small intestine to the middle of the small intestine, the middle of the small intestine to the large intestine. And then I want you to look for patterns in the food molecules. So think about these a graham cracker, for example, moving through the different organs in the digestive system. Now you have this food molecule paper already. How do these patterns help explain why the amount of one type of molecule might be decreasing by the same amount that another type of molecule is increasing? Just like we saw in the mouth. See if we can find any patterns in the data. When we're done, what we are going to do is we are going to answer our question about what we think is happening in each of the different organs. Each of these, the esophagus, the stomach, the small intestine, and the large intestine, are different organs. So what is happening in them, and what patterns do we see in the different molecules? We're going to try to identify that.